to have Boryana visiting us. She is a doctoral fellow at the University of California, Berkeley, and she did her undergrad at Princeton and her PhD at Harvard. And she is a theoretical cosmologist working on a pretty broad spectrum of topics there. And today she's going to tell us about a small-scale inference. I don't know what I think of small-scale as dust, but I feel like she's going to tell us a good definition. So, yeah, thank you.
Thank you. First of all, maybe we should get rid of
that.
Okay, cool. And I just want to get a sense, so how many people in the audience are graduate students? Okay, cool. Undergrads? Cool. Wait, sorry. I guess grad students and PhDs is the same thing. And then faculty? Cool, we made it to the list. Cool, wonderful. So I just wanted to get a sense of how many people have heard of the Synyaev-Zel'dovich effect, which will be kind of the main topic of what I'm going to talk about. Of course, this is a very CMB-centric place, so I feel like you do get a lot of talks, but I'll still start with some nice intro, I think. So yeah, first of all, feel free to interrupt me with questions. I really like that, and especially if something is unclear or if you want to get into more details, so we can also talk about it later. First of all, maybe just in case you completely miss everything about the talk, I just wanted to summarize the main things that I want to say here. So, as many cosmology talks begin, this is a very exciting decade that's going to offer us a lot of new data in the realm of both early universe, so cosmic microwave background experiments, and also in the large-scale structure. So we are anticipating a handful of these experiments in the next decade, but even already we have some really exciting data that we're in the process of analyzing, and in the next few months we are expecting some exciting results. So I'm talking specifically about the DESI collaboration, which I'm part of, so that's the Dark Energy Spectroscopic Instrument, and the joint analysis with ACT, which of course you're very, very familiar with, which is the Atacama Cosmology Telescope. And in particular, what I'll be talking about is the Synyaev-Zel'dovich science, but there is a lot more coming in with CMB lensing and so on that that I'm not working on specifically, but I'm excited about. So the main idea is that we have these amazing data that's coming in, and we want to analyze it. However, there are a lot of things that we don't know about the analysis of that data, and we can use simulations to help with that. At the same time, you might know that simulations are something that needs to be calibrated, especially hydrodynamic simulations that I'm going to mention in the next few slides. So we can also use the other way around things, where we take the data and we form the simulations, specifically about things like the baryonic processes or the feedback of active galactic nuclei and supernovae. And then our eventual hope is that we can make some really kind of good inference constraining both cosmology and also astrophysics. So on the cosmology side, there are questions related to the growth rate of structure, which reveals the secrets of gravity and dark energy, primordial number of cyanides, which is what set up the initial conditions in the universe, and also even more maybe trivial sounding things, such as how do the baryons affect gravitational lensing, which actually is a very hot topic right now. So the usual dichotomy, we think of the CMB and galaxy surveys kind of separately in the early universe, afterglow from the Big Bang, with experiments such as Planck, ACT, SO, and so on, and the late-time universe with the galaxy surveys of Sloan, DESI, Rubin, Euclid upcoming, and so on. But in reality, it's things are more related than that. So we actually have a connection between the early universe and the late universe. The obvious connection is the forward one. So, early universe initial conditions lead to late-time structures, but also late-time structures affect what we observe from that early universe. So here, for example, I'm kind of just schematically going to tell you about how the photons coming from the cosmic microwave background coming towards us, bouncing off of gas in between us and the CMB, and get received by our instruments here on Earth. And that happens to about 6% of all of the CMB photons, constraint coming from CMB polarization. So that means that about 6% of the photons get captured before they actually make it to us. And usually, in the past, people used to think of this as a kind of annoying nuisance. But nowadays, we try to take advantage of that. So that's related to the SZ, or Synyaev-Zel'dovich effect. In more detail, here are a couple of equations. So there are two types of Synyaev-Zel'dovich effect, and of course, I'm sure you have heard people talk about it, so I'm not going to spend too much time. The kinematic one and the thermal Synyaev-Zel'dovich effect. And so for the kinematic one, we can think of it as sort of just the product of two terms. So it's the optical depth, which tells us how opaque the universe is, and another component, which is the bulk velocity, which tells us with what velocity the gas is moving. And then there is the thermal component, which is the one that's proportional, again, to the optical depth times the thermal velocities of electrons. And so here's the main point. These effects are very weak, right? You have, the universe is mostly transparent. So the regions that are actually opaque are typically these dense clusters of galaxies. So mostly Synyaev-Zel'dovich effect comes from dense clusters, and otherwise it's because otherwise this gas is very diffuse and hard to see. And the advantages of that is that the gas is typically, we don't really observe that gas. So for example, X-rays give us the gas in the very dense part of the cluster where the temperatures are very high. However, SZ allows us to probe further out to where we don't have any stars, so we don't have other information coming in. So that's why it's very exciting. And another two cool features are that because it's a sort of integrated effect that just depends on how much absorption or scattering we have, it's independent of redshift. So you're getting all of these clusters at very high redshifts and at very low redshifts at the same time, and for a large range of halo masses. So it gives you a very good way of probing the gas. And why is this important? So I just want to kind of give you the sort of maybe by eye confirmation that this effect is real. So this is a result from a few years ago by the HACK collaboration, where people took the CMB map and the Galaxy Survey SDSS or BOSS, and they basically stacked the SC signal on galaxies from that survey. And when you do that, you can get from the KZ effect a map of the gas density. So this is just a stacked signal. Of course, you have to stack it because, as I mentioned, gas is very diffuse. It's hard to see. So the way we get all of that higher signal to noise is by stacking the signal. In the middle, I'm showing the TSZ, which is proportional to the pressure, and then in a different frequency, we can also see the pressure and the dust. So this is a very rich kind of tool that allows us to see both the density and the pressure. And this is for just reference purposes. The Hubble image of an object would lie very much at the center of a single pixel. So you can see that these gas profiles are actually they're very extended outside of the typical galaxies. So another way to look at that data is to show it as a radial profile. So this is a two-dimensional image, but what if we now compress it into a one-dimensional image where we just have, as a function of distance from the center, these profiles. So this is, for example, what's shown in this plot here. You can think of what's on the y-axis as the baryon profile, or the gas profile. A cumulative gas profile would just mean that you're kind of integrating the number of or your gas as you're moving away from the center, as a function of aperture or as a function of distance from the center, typically measured in arc minutes. But just as an eye guide, you can see the virial radius here with that blue line. So the virial radius of the cluster or the halo is shown here. And what is very striking to me about that image is that the measurement is here of that KSZ effect of the gas density, but in reality, but our theoretical predictions that are the most simplistic theoretical predictions of the Navarro-Franklin-White profile are much more conservative about what happens to the gas. So in other words, the gas is located a lot outside. It's expelled from the inner parts of the halo, and that is not very trivial. In fact, for a long time, people were facing this problem known as the missing baryons, where essentially we couldn't account for all of the gas or all of the baryons by just what we observed within the clusters. And part of the solution is this SZ effect. So the SZ effect pushes things out, and we can observe that directly with the, feedback processes push the gas out, and we can observe that with the SZ effect. So, okay, so...
So I have a question on this.
Yeah.
So that plot is a stack as well, or not?
Can you say that again?
Is this a stack or is this a single object?
This is also stack, yeah.
So, and what's the halo mass that you're stacking?
It's about 10 to the 13. So this is from the original analysis of the SDSS and ACT, which is from a couple of years ago. We're now improving this with the DESI data, but still the masses will be around 10 to the 13.
If you do this in 10 to 15 solar mass halos, my understanding is you get all the baryons inside the variables, right?
Not quite. I mean, let's see. So, okay, yeah, they will have some, yeah, because the potentials are lower. Yes, that's true. It's also interesting because you have a larger two-halo term for these objects, so it's a bit unclear to me what exactly would happen, but that's one of the things that we try to answer in simulations. But yeah, but you're right that relative to the one-halo term, in this case, the two-halo term is much smaller. Okay, so all right. So why does this matter? Why does it matter that we have these kinds of extended profiles around galaxies? Well, for one, it tells us that the baryons, which make up 15% of the total matter budget, do not follow the dark matter. So there is some offset, and that offset is basically basically predicated on the fact that we have this explosion from the halo center. And the interesting thing is that people who do simulations do not agree on how big that effect is. So this is a slightly older plot and a slightly hard to see. But the point here is that this is just showing, I think, 10 different simulations or 12 different simulations, 14. Okay, I can't do math. All right, so 14 different simulations, and it's just kind of showing you the wide range of predictions that people make about how big is the effect on the baryons. So how well do baryons track dark matter, and the SZ effect can kind of help us to calibrate this, and I'm going to come back to that point later on. But understanding the particular shape that this has, so this is the lensing power spectrum as a function of scale, will help us also resolve some of the issues related to the weak lensing. So you might know that weak lensing is sensitive to the total matter, so not just the dark matter, but dark matter plus baryons. And therefore, if 15% of the baryons are located at some unknown location, then that will have a huge effect on our power spectrum. And that's related to also to some extent possibly the low signal A tension, or maybe not, but maybe related to the lensing is low problem. So what is this lensing is low problem? I'm just kind of gravitating towards this topic as this was my PhD, kind of related to my PhD thesis. But so the lensing is low problem is basically the idea that if we take a measurement of the galaxy clustering and a measurement of the galaxy-galaxy lensing, and we try to fit to our galaxy clustering with some HOD model, for example. And I'm going to say what an HOD model is a bit later, but for the purposes of this example, it's just a model that allows you to paint galaxies on top of halos. And we make a prediction about the galaxy lensing signal. We will see a pretty large offset between the actual data and our prediction from the galaxy clustering. And so, so there are many proposals for what could be going wrong. One of them was what I worked on in my thesis, which is the assembly bias effect. But another one could be and is likely this baryonic effect. So again, from the original analysis by the ACT team a couple of years ago, here we can see that once we account for these missing baryons that are further away, we reconcile the differences by a little bit on smaller scales. So it has that kind of implication. And all right, so I promised to talk about simulations and how simulations can help us in the observational analysis. So I'm way more comfortable talking about simulations as someone who has spent very little time working with real data, but that will change soon. And so so we have all of these new data coming in, but do we actually know how we're interpreting it? Do we trust our methods? So one of the big questions is when we look at a given halo, say that this is the halo that we're interested in, and we're standing here as an observer, we don't actually just see that object itself. What we see is the integrated effect along the entire light cone of the universe. So we're getting contributions from objects that are aligned with our line of sight, objects that are uncorrelated, and so on. So just terminology-wise, this is known as the one halo term, is the main object of interest. Nearby clusters that are correlated are known as the two halo term, and the random intervening structure is just random structure that we want to diminish because it's just giving us noise. So we can ask the questions of how big of an effect they have, and is the model that we have adequate for accounting for this? So the model is the halo model, which I promised to talk about. And are there other properties that are that matter in understanding how the SZ effect operates in practice? And then finally, a problem that's very closely related to this observational versus simulation kind of realm is in reality, which we observe galaxies and not halos. Halos are just kind of a fictional thing in the sense that they're made of dark matter, but we don't really see that in the universe. So how much does that affect us? How much do we need to care about this? And the nice thing is that hydrodynamic simulations hold all of these answers in the sense that they have dark matter and baryonic matter, and we can track both of them because it's a simulation. I guess here I'm pausing for a second because sometimes someone in the audience will go, "Oh, but what if the simulation is wrong?" Which is a good point. The simulations can be wrong, and they probably are wrong. And as I will not show, we know that the AGN models are off, supernova models are off. But what we care about here is a more qualitative question that really does not depend on the particulars of the simulation. So, gas will be expelled. How much of the gas is expelled is a different question, but that's as much as we care about. Does the simulation have that? And so the particular simulation that I'll be talking about is the new MillenniumTNG simulation. Some of you might be familiar with the illustrious TNG project. So MillenniumTNG is kind of an upgrade on that. It's a larger simulation, has half a gigaparsec over H in box size, and its volume is about 15 times as large as the largest TNG simulation, and which makes it more suitable for cosmological analyses. It also has a very high resolution, which is great. So it's suitable for SZ, lensing, galaxies, X-rays, and on top of that, thanks to these kinds of light cone outputs that are a new feature, we can treat it as if it's real data. So we can analyze the simulation, imagining that it's ACT data. And so, okay, so the first project that I worked on with the MillenniumTNG simulations in relation to Synyaev-Zel'dovich was the scaling relations. So I want to maybe pause for 1 second here and give you a short introduction that hopefully will pay off in the next few slides of what a scaling relation is. So the scaling relation is essentially a statement that the optical depth, which you remember is an important quantity in SZ, or the Compton Y, which is the integrated pressure profile, scales almost as a power law with the mass of the halo or the mass of the cluster. And that is very useful in the sense that one of the things that people had proposed in the past was using clusters to do cosmology. So if you have a way of observing, say, the SZ effects, or observing thermal SZ or KSZ, and you trust this relationship, this power law, you can infer the mass of the halo. Inferring the mass of the halo can give you something like, the halo mass function, and you know that the halo mass function is very sensitive to dark energy, to dark matter, and so on. So that's kind of, I think, initially a lot of the motivation. Nowadays, we work with these scaling relations because they are a nice way to parameterize things and do cosmological inference. But anyways, so here I looked up on the website, and there are people who are doing FRBs, so I put in some FRBs. But one thing that's kind of interesting is that when we say optical depth, we mean very different things depending on what we're measuring. So the X-ray community, when they measure optical depth, they're measuring the signal that's coming from basically the innermost part of the halo. So they're really not that sensitive to anything outside of that virial radius. When the FRB community says we're measuring optical depth, they're actually measuring everything along the line of sight, not just your object, but everything else. So you will see that the X-ray line is here, and then the FRB line is much larger than that, because you're picking up all of that additional structure. When we say in KSZ that we're measuring optical depth, we're measuring something kind of in between. And I'll say why that's the case, but just before that, I want to also pay attention to this break in the power law. So as I mentioned, we often say that the scaling relation is the power law, but that's not quite true. In fact, we see that there is a deviation from that around 10 to the 14 solar masses, and that's due to feedback processes. So observing that, for example, in the real universe gives us another way of comparing with the simulation and saying, okay, our supernova feedback is off, or it's matched well, or something like that. But anyway, so back to the question of KSZ. So why is the KSZ signal kind of in between? I'll give you a sort of intuitive, I think, explanation of why that's the case. So the KSZ signal, essentially, if you remember, it's optical depth times velocity. So what happens is that you're picking up a lot of structure that's around your halo, which is infalling towards your halo. So imagine, a large-scale structure. You have some cluster in the center, and then there's structure infalling towards that cluster. And it's essentially it has its own optical depth, and it's going to be correlated with the motion of your cluster of interest. So what's going to happen is you're going to get an enhancement. So that's what's happening here. We have an enhancement over the X-ray signal, over the intrinsic signal. But as we get to higher and higher masses, where we have a very massive cluster, and things infalling from either side, they basically cancel. So at this point, you're not actually adding much to that signal, because your velocity on one side is positive, on the other side it's negative, so you're just getting the intrinsic signal. So that's what's happening here on the very massive band. But this is not very satisfactory in the sense that all these three measurements are trying to measure the optical depth of one cluster. Can we do something about this? So what's proposed in the literature are two main ways of dealing with this. So one can subtract the uncorrelated contributions by, for example, doing the following. So you can point your telescope, or in this case, simulation, at a random part of the sky, and just measure the signal in some aperture layer, and subtract that from the measurement. And the problem with that is that you sometimes will get a bias, because some of the regions will be some of the regions will have more gas or less gas. So that's a very noisy way of doing things. And I actually did not include it in the slide. I thought that I did. So in any case, it doesn't do as well as the second way of dealing with things, known as the compensated filter. So it's used in, again, the original act analysis that I was mentioning to you. The initial idea, and maybe that's a very nerdy thing, but I think it's interesting, is that the compensated filter did not really think much, the people did not really think much about this 1 halo, 2 halo random contribution. What they were mostly concerned with was the primary CMB signal. So what happens when you look at the SZ is that SZ is a very small scale signal, and the primary CMB signal varies on much larger scales on the sky. So what people wanted to do was simply divide out, or I guess subtract out that variation of the primary signal. So that was the main goal of the compensated filter. However, it turns out that if you apply that, and this is what's shown now here on the plot, you actually get a pretty good agreement between the FRB signal measurement and the KZ measurement. So in other ways, in other words, what you're left with is a slight kind of difference between these two curves attributable to the 2 halo term. So remember the 2 halo term, that's the one that comes from the correlated structure nearby. So that's what we still need to deal with. And yeah, okay. So yeah, I will come back to that point of the 2 halo term, but it's not a very trivial thing to model, and it's probably one of the things that we really need to understand well if we want to do cosmological analysis. For astrophysical analysis, we can proceed without necessarily understanding it, but anyways. Okay, Renee disagrees. Okay, anyways, so now I need to make a compulsory digression. So far I've been showing you the mean scaling relation between the, say, optical depth and halo mass, but there could be other things that the SZ signal depends on. So my PhD was centered on this question of galaxy assembly bias. So that's the question that typically we say that the number of galaxies in a halo is basically a function of its mass, but that's an oversimplification. And if we make that assumption, then we're actually end up being quite away from the true clustering. So there are additional properties that we need to take into account. These are known as assembly bias properties, and historically people talk about concentration as one of them. And in my PhD I showed that concentration is not as important as a parameter related to the environment of the halo. But why is this important for SC? After all, this is galaxies and we're talking about the CMB. Well, it's because, again, we're marrying large-scale structure with the CMB. So we use our galaxy surveys, which have their own biases and assembly biases, and we are stacking the signal on top of these galaxies. So any kind of bias that they have will reflect on the SZ that we're inferring on the SZ signal. So again, this is the optical depth from before versus the halo mass, and what I'm trying to show here is that the mean relation that I was showing you before actually has some kind of intrinsic scatter, and that intrinsic scatter can depend on concentration. So this is, for example, showing if we select the most concentrated halos and the least concentrated halos at the fixed mass point, so say that you pick halos around this region of 10 to the 13, and you now ask what is the SZ signal, you will find that for the most massive objects, perhaps the intuitive understanding holds. So the more concentrated objects that have more kind of a higher density inside the cluster will have a stronger SZ signal or a bigger optical depth. But when we get to the smaller halos, then that relation inverts itself. And what is this inversion related to? So I personally, as a sort of hypothesis, and think that it has to do with the AGN, or the supernova feedback. The logic being the following: we know that when we have a very concentrated halo, that means that it has a lot of structure that's being accreted onto the central region, and that accretion is actually activating the AGN, or activating the feedback processes, and pushing away the gas even more readily than before. So in this region here, you're evacuating the gas from the inner sides, and that's why you see an inversion compared with the outer regions.
So this result is from your simulations?
That's from the simulations, yeah.
So is it too expensive to go back and run a different feedback model? Is that part of the problem? Because you can check whether the agent turning on was making a difference.
Right, so that's a good point. It's not that it's expensive, but on the market there are very few different models. I think there may be, currently maybe 4 or 5 different hydrodynamical models that are good enough to kind of tackle these questions. But yeah, you need to start with the same initial conditions and so on. That is a project that, for example, the Camels team has sort of tackled, where they have Simba and MillenniumTNG. Now I think they're including Ariel, but I forgot the other kind of simulation names, but they are working on this, but it's on much smaller boxes, so you can't really cover that kind of huge range of halos. But you're right, that's basically one of the things that needs to be understood, is how much of this is, just a prescription question. Yeah. Okay, and so secondly, the other thing that I wanted to mention is also the environmental effect on optical depth. So specifically optical depth inferred from the KSZ. So we find that actually the dependence on optical depth is pretty strong in the KSZ signal, and the dependence on the environment is very strong in the KSZ signal, and we have investigated what's causing that, because maybe you think that it should be as strong as the effect of say concentration, but it seems like there are some kind of nonlinear velocities that are affecting the basically the inflow velocities near your cluster, and that's a scale-dependent statement. So that's very strong and very affected on the 2 kiloterm. So if you want to model the 2 kiloterm correctly for KSZ, you shouldn't just care about the mean kind of behavior. You should also take into account how it responds to the sort of large-scale environment. And so that, I think, makes it even more tricky, because it's already a very tricky problem, this 2 kiloterm, especially on very nonlinear scales. And now you're adding in this kind of nonlinear velocity effect, and that's making it a bigger nightmare than before. Okay, any questions about this before I move to more pleasant topics? All right, so to wrap up the sort of simulation chapter, I wanted to just mention, if you remember from my slide of interpret our observations correctly, I mentioned that we stack on galaxies and not on halos, and that can be a problem. This is known as the so-called miscentering effect. So ideally, you want to be stacking at the center of the halo, because that's where your signal is basically symmetrically oriented, or roughly symmetrically oriented. But in the real universe, you can't really distinguish between galaxies and satellites and centrals. So you can't really say which galaxies live in the central in the center of the halo and which live on the outskirts. So you just stack on all of these objects. And so how big of an effect is that in simulations? So again, this is, I think, a very robust test, in the sense that the simulation has centrals and satellites, and it has that kind of spherical behavior, so we can directly see how big of an effect it has. So here I'm showing again the optical depth as a function of arc minute, as a function of distance from the halo center. If you remember at the beginning, I was showing this cumulative baryon profile, so that's the equivalent that you can get in a simulation. And what we're seeing is that, because if we split the galaxies into centrals only and all of the galaxies, so centrals plus satellites, then the curves are not overlapping. In particular, in the highest luminosity bin, where most of the galaxies are centrals, the two curves, the purple dashed and the purple solid line line on top of each other. But as we move to smaller galaxies, so with smaller luminosities, then that starts to become a bigger issue. So for example, in the medium bin of luminosities, which corresponds to the typical DESI galaxy, you see a gap of about 20%. So this kind of miscentering effect can basically change your normalization by about 20%. So that's something to take into account as well when analyzing the data. And okay, any questions on the simulation side? All right, so I promised to talk about more pleasant things. So my pleasant things are the kind of upcoming and ongoing projects that I'm working on with the ACT and DESI data. So ACT and DESI, two collaborations that have now reached a memorandum of understanding, to the headache of all of the spokespeople and higher ups. But we were very happy about it. And so first of all, we get an upgrade in the data department. So this is showing the comparison between Planck and ACT. So you can see that it's kind of much less granulated. You get a lot more really nice. Basically, you get a lot more detail and a lot better resolution. So that's one of the departments in which we improve. Here I'm just showing what the TSZ clusters look like in those maps. The other department in which we improve is the change between SDSS and DESI. So SDSS had about 700,000 or 500,000 galaxies, and now with DESI we have 7 to 10 million LRGs. And then the main galaxy sample, which is the equivalent of the bright galaxy sample of DESI, is also seeing an improvement of a factor of 100. So it's a big data improvement. And of course, that our signal to noise is proportional to the square root of that, of the number of objects. So it's really helpful to us. We also have pretty good overlap with ACT. So currently we're here where, currently the DESI is in year 1 stage, so the overlap is about 1200 square degrees, but eventually we're going to get up to almost 9,000 square degrees, which is very exciting. And so now I want to say a few words about the ongoing work that I have. I have preliminary results that I can show in private. So the first thing that I'm working on is the kind of update on what I was showing you with these stacks. So I never said how we do this, so let me spend just a couple of minutes in explaining that process, because again, I think it's very interesting. So the process is the following. You have the CMB map, and you have your galaxy survey. And if you're interested in the KZ signal and you just stack on your galaxies, you're going to get 0. Why are you going to get 0? Because the KZ signal is proportional to your velocity, and your velocity sequence is likely to be pointing towards you, the observer, or away from you. So what you need to do is some kind of clever thing to essentially divide out the velocity dependence. So what we do in these kinds of stacking analyses is we first perform a step of reconstruction of the velocity. So what that means is that you take the galaxy survey, you solve the continuity equation. So your galaxy survey provides you with the delta galaxy, the galaxy density field. You solve the continuity equation and you get the velocity field. And now you have the velocity field from that kind of reconstruction and also from the KZ effect. So if you just weight by your objects by that velocity, you essentially get rid of your sign dependence, right? Because if you have negative velocity, multiply by the reconstructed velocity, which is hopefully also in the negative direction, then your signal becomes positive. Okay, and then what you do is now that you have stacked everything, your signal becomes proportional to the optical depth times this the times the velocity RMS. The velocity RMS we can get from linear theory, and what that leaves us with is an estimate of the optical depth. So that's what I've been talking about. On the other hand, the TSZ measures the optical depth times the temperature, that's the pressure essentially. So if you divide out this term by this term, you can also get the temperature. And that's very powerful because we really want to be able to constrain our models of temperature and Boryana physics. So that's what I'm currently working on. Those of you who maybe are more experienced will say, okay, why the hell are you doing this with flow Z's, photometric redshifts? So photometric redshifts, as you might know, are much more noisy. Whereas DESI is a spectroscopic survey, so you have exact three-dimensional location. The reason is that we fought over projects, so I took the photometric redshift one. But it comes to the advantage that I can use the full DESI and ACT footprint. So actually my signal to noise will likely be higher than the spectroscopic signal in the first few years of DESI operation, or at least so I was told. No, I think that's going to be true. But so that's kind of the reason why I am doing this with PhotoZs. And there is another student of Manuel Schans who is working with the spectroscopic data. So you should be looking out for both of these analyses. And we'll have improved models, so that's really exciting. And I know some of you are interested in cosmology for some reason. There's also another project that I'm going to be working on related to the growth of structure. So your KSZ signal is proportional to the growth rate times the optical depth. So if you have a way of getting rid of the optical depth, you can also constrain the growth rate. This is just showing the growth rate as a function of redshift and various constraints coming from people's analyses. We don't have a lot of points here in the low redshift region, but we have very different modified gravity predictions. So if we actually measure with good certainty of what happens to the growth rate low redshifts, we can rule out some of these models. And so one of the other projects that I'm working on with David Alonso at Oxford is basically taking the bright galaxy sample, so that's the low redshift sample of DESI, and performing a analysis using a pairwise velocity estimator. And that's many buzzwords, just here for people who might be familiar, to infer the growth rate. And for that step, we need to assume something about the optical depth, which is where the simulations play in. So that's that idea. And okay, so I'll leave you with some summary and then other things that we can talk about, but please feel free to ask me any questions. So, all right, so the summary is that hydro simulations are helpful. They allow us to kind of discern between different optical depth measurements tools, allow us to figure out the best way of removing random contributions and modeling the 2K term. They allow us to constrain or understand the miscentering and come up with tools to overcome that issue. So they're really helpful in that way. And I have other ongoing projects with MillenniumTNG related to the 2K term, but that's challenging, and I would love to talk to people if they have ideas. And then the DESI MOU is providing kind of opportunities for new analysis and retouching data, so that's exciting. And I'm just going to leave you also with relevant work that you might be interested in hearing about. In particular, I can talk about the kinetic effective field theory. If I don't die before that, sorry. It's going to get some water.
Probably a good break and internalize the slide.
Yeah, exactly.
It's almost as if I hold a chronometer. Every time I give a talk, at the 50th moment, I lose my voice. 50th minute. Anyways, okay. Yeah, so if you have any questions, please let me know, and you can still sign up to meet with me today or tomorrow. And yeah.
We have any questions here or online? Raise your hand. Cool. I can see you. I can see you.
Yeah.
Thanks for your talk, really interesting. I just had a maybe naive question. When you're stacking, does the distribution along all the stacked pixels for a single line of sight, does that follow a Gaussian distribution, or?
Oh, well, you mean if the gas profile follows the Gaussian distribution?
So just take one pixel from all of your stacked images,
Yeah.
just along one pixel that you're stacking. Does that follow a Gaussian distribution, or does it have all these weird higher order moments just from stacking different kinds of halos?
Oh, I see what you mean. Yeah, I guess it depends on what you're stacking on. Ideally, you're stacking on very similar objects, so you want to basically have as little variation in that profile as you can. Or if your data is very rich, then you want to be splitting it into, say, different redshifts or halo masses or luminosities. So yeah, it depends. If you're doing it kind of randomly, then I suppose it would follow Gaussian. But if you're doing it in a more controlled way, then it should.
Thanks.
A question mark, if you go back on the slide. Slide. Well, actually, that one, what's the DGP stand for?
Okay, well, I looked this up specifically for this question. So it's the, oh no, now I forgot it. Okay. It's a model by Bali, Gabadadze, and Parati.
Right.
Yeah, exactly. No, that's why I do
Right, okay.
this. And it's a 2000, it's a model from the year 2000 of modified gravity that's gotten quite popular.
Right.
Yeah. It's pretty wild, as you can see.
Yeah. And you're not claiming to rule it out yet, I guess.
No, I mean, as you can see, growth rate and F sigma 8 specifically has been a topic of a lot of contention, and people are finding these low signals, right? So some people can even see that as some evidence for modified gravity. Of course, there are probably more trivial explanations, or I shouldn't be saying that, but yeah.
The other question I had was, so if you're trying to constrain feedback, I gather you're talking about 10 to the 13 solar mass halos.
Mm-hmm. On average, right? Yeah.
On average, yeah.
Yeah.
I mean, I remember the state of the art a few years ago that was the best you could do. You really didn't have much signal in 10 to 12.
Right.
But you've got a lot more galaxies now.
Yeah.
So what's the future for that look like?
So going down to 10 to 12, I mean?
Yeah. Because that's where people think most quasars sit, right?
Right.
That's when they're actively doing things. Maybe they don't actually show up much in essay until they're older. But.
Right. I mean, there's also redshift dependence to that statement, right?
Well, I know. Is there?
I mean, like AGN is more active at redshift of 2.
Yeah, but they're still. I think the claim is they're still in 10 and 12 solar mass halos, sort of at any redshift.
I think
that's of course oversimplified, but I think that's what most people would say.
I tend to think of it more as, between 10 to the 12, 10 to the 13, you're sort of dominated by supernova feedback, and then past 10 to the 13, 10 to the 14-ish, you started being dominated by AGN. That's kind of in the low redshift universe. And then going backwards, I need to think exactly where that scale transitioning is happening. But in terms of state of the art of 10 to the 12, so for example, these BGS objects are, what I'm very hopeful will be able to give us some of that information around 10 to the 12, 10 to the 12.5. The issue there is that the signal is very weak. So your beam is, for example, the beam size is one of the things that you will run into as an issue.
Getting beam dilution.
Yeah, and on top of that, it's your signal is proportional to the halo mass, so you're really struggling, and then once you start stacking, you will be dominated by clusters nearby, especially if they're more massive. So I think it's complicated, but it's doable. We'll have 10 million objects, so I think that's a pretty large number if people can analyze it well, right? Yeah. I don't know if that fully answered your question, but yeah.
Thank you very much for your talk. Going back to the sort of initial conditions of the simulation, I just wanted to know, did the MillenniumTNG simulation use the same initial feedback model as the illustrious simulation?
That's a good question. Illustrious or illustrious TNG? TNG. Okay, so essentially TNG and MillenniumTNG are very, very similar, with the difference that we have turned off magnetic fields for MillenniumTNG. I don't know why, numerical reasons. But other than that, we have checked that they're very, very similar to each other. The resolution is a little bit worse for MTNG, but it doesn't seem to affect things too much. Compared with illustrious, of course, it's a very different model. Sorry, I know I'm not. That's not that interesting to anyone else, but here on this plot, the craziest line comes from illustrious. So this is the illustrious supernova feedback, which is really different from anything else. And again, because I guess I like taking digressions, if you take a look at the latest Alexander Amon and Georgia Statio's papers, they claim that actually to resolve some of these low sigma 8 tensions, you do need something really crazy like this. So I guess what I'm trying to say is it's not clear how crazy this is, but yeah.
Any other questions? I have one. Earlier at the beginning of the talk, we were talking about this happening, the two-halo effect. When you're trying to explain a bit, like what is a two-halo effect when you're looking at a single?
Yeah, absolutely. Yeah. I'm glad you're asking. You're opening your camera, so all right. So essentially, the schematic way of thinking about it is you have some object that you're interested in, which is say this halo here, and you know that the structure around it, all the halos around it are clustered in some way. So you have some clustering signal. Once you move away, very far away, maybe the correlation diminishes. But for the structure nearby, you have a two-halo component. So basically, you're likely to find with some probability halos nearby. And so when you're measuring the signal in the CMB, and that halo has its own gas profile, that halo has its own gas profile, what you're actually measuring is the sum of the two, or you're integrating the signal along both of them. So the CMB photon would have to both pass through this guy and also through this guy without getting scattered, or would have a higher chance of getting scattered by either of the two. If this halo, for example, was sitting on this side, and we were just measuring the signal again in some small aperture, then we wouldn't care about it necessarily. But because this is random, isotropic, we then care about the halo. So when we say 1 and 2 halo, it's really just a term for the clustering around the halo. Yeah. So
multi-halo.
Yeah, exactly. So it comes from the fact that when we do 2-point correlation functions, you care about pairs, so you have a 1 halo and 2 halo term. I don't know if people say 3 halo, maybe they do. Okay.
Any other questions? Just check online. So, okay. Well, thank you so much for the great talk.